We will look at different types of radical expressions. Let's first start at simplifying radical expressions. So the nth root of x to the n equals x if n is odd, n is the index, and that's because the nth root of x to the nth can be rewritten as x to the nth to the 1 over nth power, because we're taking a power to a power, we multiply the exponents. N times 1 over n is 1, so that becomes x to the 1, or just plain old x. But the nth root of x to the n equals the absolute value of x if n is even. So let's look at an example. Let's look at the square root of 16x to the 8th. So first, let's write each factor as perfect squares. And we're looking at perfect squares here because the index on our radical is 2. We don't see it here. When we don't see an index, the index is 2. So I can rewrite 16 as 4 squared, and I can rewrite x to the 8th as x to the 4th squared. If I couldn't rewrite those as if they weren't perfect squares, I could possibly rewrite part of them as perfect squares, and I'd have parts that were not perfect squares. But here they were perfect squares. Then we'll rewrite as one expression squared. So I can rewrite this as the square root of 4x to the 4th squared. And then simplify. The index n here is even, it's 2, so we need absolute value. So this simplifies to the square and the square root are inverse operations. So we've got the absolute value of 4x to the 4th. In this case, 4 is always positive, and x to the 4th is always positive, so we don't really need the absolute value bars, and we can drop them, and we can just rewrite this as 4x to the 4th. Okay, so now let's look at an example of adding radical expressions. And if we were subtracting, we would look at it very similarly. So our first example of that would be the square root of 12 plus the square root of 75. So first, we will simplify the radicals. So neither 12 nor 75 are perfect squares. The largest perfect square factor of 12 is 4. I can rewrite it as the square root of 4 times the square root of 3. The largest perfect square let's finish simplifying that. So the square root of 4 is 2, so that can be simplified to 2 radical 3. The largest perfect square factor of 75 is 25. I can rewrite the square root of 75 as the square root of 25 times 3. The square root of 25 is 5, so that can be simplified to 5 radical 3. So now that is simplified to 2 radical 3 plus 5 radical 3. Then we can combine similar radicals. Now, both of these expressions have radical 3. If the radicals were different, we would not be able to combine them, and we would be done. But they both have radical 3's, so now we can combine the 2 and the positive 5. 2 plus 5 is 7, and we get 7 radical 3. Okay, let's multiply two binomial expressions with radicals. So for example, the square root of x plus 6 times the square root of x minus 1. We're going to distribute. So I could take the square root of x times the square root of x. That would be x. The square root of x times negative 1 is negative square root of x, or negative 1 square root of x. 6 times the square root of x is positive 6 square root of x. 6 times negative 1 is minus 6. And now I can combine my like terms. So I only have one term that's just an x, so I have an x. I have one constant, so I have a minus 6. I have two terms that have a square root of x, so I can combine those. Negative 1 radical x plus 6 radical x gives us 5 radical x. So I have x minus 6 plus 5 radical x. Okay, finally, let's look at a division problem. But division with radicals isn't really division. We call it rationalizing the denominator. So we're basically going to be changing the form and not really changing the value, but not really doing division either. So for example, we'll take 2 over 1 plus the square root of 3. So we don't really like to have radicals staying in the denominator of fractions. So what we're going to do is we're going to find what's called the conjugate of the denominator. So if our denominator is 1 plus radical 3, our conjugate is going to take the same expressions, the 1, the radical 3, but the operator in between them will be the opposite. So my conjugate is 1 minus the square root of 3. So only the operator in the middle is the opposite. And then I'll multiply the original expression by a fraction that contains the conjugate in both the numerator and denominator. This is multiplying that original expression by a form of 1. So I've got my original expression, 2 over 1 plus the square root of 3, and I'll form a fraction out of the conjugate, so times 1 minus the square root of 3 over 1 minus the square root of 3. That's a form of 1. And now I'll multiply them. So in the numerator, I'll have 2 times 1, which is 2. 2 times negative square root of 3, which is negative 2 square root of 3, or negative 2 radical 3. I'll multiply my denominators. So I have 1 times 1, which is 1. I have 1 times negative radical 3, which is negative radical 3. I have negative radical 3 times 1, which is positive radical 3. And I have radical 3 times negative radical 3, which is negative 3. So nothing in my numerator can be combined at the moment, but in my denominator, my radical 3's will cancel out, and I'm left with 1 minus 3, which is negative 2. And let's simplify this. To simplify this, I'm going to separate it, so I'll have 2 over negative 2 plus negative 2 radical 3 over negative 2. And now we can simplify it a little bit more easily. 2 over negative 2 simplifies to negative 1. And in the second fraction, the negative 2's cancel, and we have plus radical 3. So a different form of our original expression, 2 over 1 plus radical 3, is negative 1 plus radical 3. That's called rationalizing the denominator. So we no longer have a radical in our denominator.